Assalamualaikum and salam sejahtera. We are from Group 9 and today we would like to present our assignment 2 for MKW 4023 Financial Forecasting. For question 1, by using data from year 1 to year 8 as in-sample data and year 9 to year 10 as out-sample data, first calculate the data. 2. Write the equation of the best selected model. 3. Calculate the map for in-sample and out-sample data. And last one is plot the time series graph. For question 1, we calculating and analyzing the value of delta, which is a smoothing constant used in exponential smoothing forecasting. In this question, we use a time series dataset and apply smoothing technique to reduce fluctuation and identify the general trend over time. After we calculate, we get in-sample map is negative 3.98775 and for out-sample map is negative 2.8714.
Here, quick summary of the key finding. To begin, we set B is 2, which represent the number of groups used to the use of the data aggregation and analysis. The total value of column E is calculated as 74166,351. Similarly, the sum of the column F is 474213. This the total represent of the foundation finger for the calculation. The average value for Y, the next as Y bar is 168,052.9. For the Z, the average Z bar is 3984.98. Thus, average provide insight into the central tendency of our dataset. The variance as Z is computed as 78432.32, representing the square deviation from the mean. Using the variation, the standard deviation is divided as 0.9087, which reflected the spread of the data around the mean. For the delta value calculated to adjust average deviation is 365.3028. This value ensures the precision of our analysis. For the regression statistic, the model explained 39.53% of the variation is statistically significant. Each 1 unit increase in the independent variable lead to an increase of 2,528.56 unit in the independent variable. So the whole answer for this statistic regression is the model is valid and the independent variable has a strong impact. For the Marima model analysis, the Marima model use one differences and a seasonal component of order 1, 2. So AR1 and AR2 are statistically significant with p-value of 0.000 and 0.002 respectively. So SM8 1, 2 are highly the important of seasonal factor. For the conclusion, Marima model is effective for forecasting, which a seasonal component playing a significant role.
Hello, I am Bill Carson. I want to present question 2. By using data from year 1980 to year 2000 as in-sample data and year 2001 to year 2008 as out-sample data. First one, we need to calculate the delta and then write the equation of the best selected model. After that, we need to calculate the map for in-sample data and out-sample data. Lastly, we need to plot the time series graph. And then for the next slide, we calculate the mean absolute percentage error or MAP to evaluate model accuracy. The in-sample map is 31333, indicating the average error during model fitting. The out-sample map is 91330.5, showing the error when forecasting future values. And then we calculate the average of transform Z value Z bar, which come out to be approximately 3434.68. Then we get the standard deviation of the Z is 2164.28 something. So from this we get the value of delta is 73.8293 something. After that we compute one more time, then we get the another standard deviation of Z is 178471.11338. So from this we get a delta is 1. And then with a different z bar value of 697, we calculate a new delta value of 0.75. This shows a relative comparison between the two sets of scenarios, possibly measuring how much more or less variance one has over the other. The graph shows a positive linear trend between the independent variable, likely time or even number, and electricity generated. Represented by the blue dots, the linear regression equation indicate that electricity generation increases by approximately 3733.3 units for every unit increase in the independent variable, with an initial intercept of negative 8115.4, which might not be meaningful in practical terms. The dotted line reflects of the overall trend, suggesting a consistent growth in electricity generation over the observed period or event. So this model, a seasonal autogressive pattern, SAR, we get that the coefficient is negative 0.9971, that which is p-value is equal to 0.000. It is highly significant. So for the constant, we get a coefficient x7939. For the p-value is 0.000. It's also the highly significant. So this model captures the seasonal autoregressive pattern effectively, SAR 12, and includes a significant constant term. It is simplest mode with only two parameters, both statistically significant. By avoiding unnecessary complexity, it balances accuracy and interpretability, making it more robust for forecasting. Lastly, for the graph, the time series plot of YT show a clear upward trend, indicating that the values of YT increase steadily over time. The graph begins at a moderate pace but accelerates significantly around the midpoint, index 15 until 20, suggesting a period of rapid change. Toward the end of the series index 25 to 30, the rate of increase slows slightly, hinting at a potential stabilization. This overall pattern may represent a process with initial steady growth, followed by a rapid surge and possibly leveling off.
Hello everyone. Today, I will be presenting our analysis for question 3, which focus into forecasting using the Hall-Winter two-parameter double exponential smoothing. For part A, our task was to find the least square estimate for beta null and beta 1 using the marine fish landing data from 1954 to 1973. This historical data serve as our in-sample data for setting up our initial trend. As you can see from our calculation, we determined that the slope coefficient beta 1 is 14569.38. This indicates a positive linear trend in marine fish landing over this period. The y-intercept beta null is calculated as 55330.15. This value established the initial linear relationship in our data, which is foundational for the exponential smoothing method. Moving to part B, we used Hall-Winter double exponential smoothing to forecast marine fish landing from 2000 to 2008 for first step, second step, and third step. The table shows actual and forecast values, while the graph compares them. Blue for actual, red for first step, green for second step, and purple for third step. The first step forecast is closest to actual data. As the forecast steps increase, the lines become smoother and slightly less accurate, which is expected. Moving to part B, we used Hall-Winter double exponential smoothing to forecast marine fish landing from 2000 to 2008 for first step. Finally, in part C, we calculate MAPE to measure forecast accuracy. The results are 11.07% for first step, 10.96% for second step, and 11.3% for third step. This shows our forecast divide about 11% from actual values, which is reasonably accurate. As expected, error slightly increased with more forecast steps.
For question 4, this question focus on using the multiplicative winter method for time series forecasting. This is all the formula provides that we can use to solve the question. For this question, we are given the smoothing parameters which are alpha equals to 0.115, beta equal to 0.1 and gamma equal to 0.05. And here also given the time series data we are working with for this question. We have the data for 4 years and our goal is to forecast for year 5 and year 6. To implement the multiplicative winter method, we first need to initialize our components. As we can see here, we have determined the initial value for alpha null 0 and beta 1 0. We also calculated the average values for the initial periods denoted as y bar 1, y bar 2, y bar 3 and y bar 4. The table also displays the normalized seasonal factors SNT0 which are crucial for incorporating the seasonal patterns into our forecast. For example, for the first month SNT0 is 1.240769646, indicating a strong seasonal uplift in that period. And now, let's look at the results of our forecasting. This table presents our calculated forecast for year 5 and year 6. We generated this prediction by applying the multiplicative winter method using the given alpha, beta and gamma values. The graph below visually represents our forecast alongside the actual historical data. As we observe, our forecast attempts to capture both the underlying trend and the distinct seasonal patterns present in the historical time series. The peaks and troughs in our forecast align with the observed seasonal fluctuation. We also calculated the sum of error for our forecast, which provides an overall measure of how well our model performed. The value of the sum of error that we obtained shows that the data with this relatively large sum of error suggests that while the model successfully captures the general pattern, there are still significant differences between our forecast and the actual values. In summary, our forecast for year 5 and year 6 clearly show the expected seasonal variations. The calculated sum of errors indicates that there's room for improvement in accuracy.